All right, you have out your notes for lecture 8. I'm going to do an example. You're going to do an example where we kind of put this stuff together and we find the median and the mean for a continuous set of data. Okay, so there we have our data set of weights of adult hippos, and this, of course, is a continuous data set. I think the lowest one is somewhere around 3,000 pounds, and the biggest one is somewhere over 4,000 pounds. And the weight could be anything in between there. I'm not going to count, I'm going to weigh. Get these little guys up on a scale and weigh. So I'm actually doing a measurement, right? Now, you look at those numbers, they're all integers. Just like in the last example, they were all to the nearest tenth. It kind of looks like discrete data, right? In fact, if you think about when we measure continuous data, we're always going to measure it to a certain accuracy level. And so if we don't go beyond that accuracy, we can't get all possible values. So it's almost like every piece of data we look at is discrete, right? But the truth is, the values could be anything in the interval, and we have to think in terms of being able to measure down to arbitrary accuracy and so arbitrary precision. And so they really are, it really is continuous data. All right. So what do we have? The lowest one is somewhere around 3,000 pounds, I think. So there's no reason to go below 3,000 pounds. And how wide should we make each class? What should the class width be? So I'm going to say lowest, let me see, make sure I'm still inside here. The lowest endpoint, left endpoint, probably 3,000 pounds is good. And what's a good class width? Well, again, it's to some extent it's up to it's up to the person who's actually summarizing the data. I suggest that since we go a little over 4,000 pounds, and we typically don't want, fewer than maybe 4 bars and more than 10 or so. If we can get kind of in the 5 or 6, 7 bar range on our histogram, that's good. So I think a good class width would be 200 pounds. We'd go up by 200 pounds, and that's my judgment. And you might do something a little bit different, but that's what I'm going to do here. Okay, so we have our class, and we have our. I keep checking to make sure I don't go off. Our frequency, and then we have our relative frequency. Okay, so our first class starts at 3,000. Let me give myself a little more room. 3,000 up to what? The next class, remember, class width starts at this class width plus, or this class point plus the class width. So it starts at this left endpoint, and the next endpoint would be go up that much, 3,200 pounds. All right, so what do I go up to here? Well, I want to go up to right below this, 3,100. And since I'm only going up, the data only goes out to the nearest integer, I don't need to go to tenths or hundredths. I can just go to 3199, right? I'll grab all the data points that way because there's nothing in between 3199 and 3,200 because I'm not measuring any data out to the nearest tenth or anything, only to the nearest whole number. Okay, so the next class here will be 3,200 to, I add the class width over here to get 3399, and then it'll be 3,400 to 3,599. Never forget, the class width doesn't go from the left endpoint to the right endpoint. It's so tempting to think that. It goes from the left endpoint to the next left endpoint, from the left endpoint here to the next left endpoint, or from the right endpoint here to the next right endpoint. From the right endpoint here to the next one, or from the midpoint to the midpoint to the midpoint, as we saw before. All right, so 3,600 to 3,799, 3,800 to 3,999, and 4,000 to 4,199, and I think that gets them all. All right. If you want to pause me and go through the data set and see if you get the same frequencies I get. I get 148642, 148642. 2. And that gives me relative frequencies of 0.04, 0.16, 0.32, 0.24, 0.16, and 0.08. All of these data sets have 25 numbers in them. That's just because I like the number 25. It's not too big and it's not too small. So that's why a lot of the data sets that I come up with have 25 points in them. Let's see. Let's get the class midpoints. And I kind of went off a little bit there. It says last midpoints to you, but that's class midpoints. And to get the first one, I will take left endpoint plus right endpoint and divide by 2. And that gives me 3,099.5 pounds as my first class midpoint. What's the next one going to be? I'll take the average of that and that. I'll add them up and divide by 2. That's always going to give me what's exactly in the middle of those two. Or I can just take the class width and add it. So that would be 3299.5. And doesn't that make sense? In between 3,200 and 3,399, yeah, 3,299.5. And then 3,499.5 for the class midpoint there. And let's see, I can get maybe one more in, 3699.5 for that one. And I guess I got to go over here now. 3899.5, and then 4099.5. There are my class midpoints. That will help me draw my histogram, which I don't know. I may not do that here. I may just leave you to do that. What are the class boundaries? Let's see. I guess I can fit those in. Let's see, how much room do I have? I'm doing all right, I guess. So I like to go below, but I can't, so let me just go right here. What are the class boundaries? And again, these are kind of, BDRIES is my abbreviation for boundaries. These are kind of, I don't stress them that much, but if you were drawing a really nice, well-detailed histogram and you wanted to put, you know, where the left side and the right side of a particular bar were, that's what these class boundaries are. Okay, so I want to go in between 3199 and 3200, which obviously is 3199.5, right? 3,199.5, halfway between there and there. And that's where the first bar and the second bar are going to touch. Then I just add the class width, then I get all the rest of them. So it's 3399.5. 3599.5, 3799.5, 3999.5. That one represents where the bar for this class and the bar for this class will touch. Well, what about the right side of this bar? The answer is go up another 200 and you get 4199.5. It doesn't touch anything, but it's the right bar here. Well, what about the left bar way over here? Well, just go down 200 and you get what? 2999.5. So there are all your left and right sides of your bars. There are all the class boundaries. So if you're drawing your histogram, you could label all that stuff just real nicely here. Let's find, I say here that you should find the median and the mean of this data. You don't generally find the mode of a small sample of continuous data points because they're going to be kind of all over the place, right? Because they're continuous data. You don't have just a few discrete values. You have an infinite set of possible values. So you don't usually worry about the mode. We'll later see that there's a way to think about the mode for continuous data. But right now, what's the median just of this data set? Well, it's not too hard to figure out. There are 25 data points. So again, I want the 13th one. If I go from lowest to highest, if I arrange them from lowest to highest, I want that 13th one. So look here. I do 1 plus 4 is 5 plus 8 is 13. I can see that the median, the 13th data point, will be the largest data value in this class, won't it? So I got to dig through and find that, and it turns out to be 3584 if I didn't make a mistake. All right, what about the mean? The mean, actually, I think, yeah, that's all right, I got it in here, don't I? Yeah, I'm doing good. Doing well, sorry. The mean, well, if we do it the old-fashioned way, You take the first data point, which is 3,400, plus the next data point, which I'm just reading from the list. I'm not reading them in order, from smallest to biggest. I'm reading from the list here. Plus the next one is 3,672 plus ... If we add them all up, the last one is 3,686, and divide by the total number there are, we get the mean, which turns out to be 3,600.2 pounds. 3,600.2 pounds. But let's do what we've done before, which is where we used the relative frequencies. We have a little bit of an issue though. Before, when we had discrete data, each value had a relative frequency. I take that value times its relative frequency, do that for all of them, add them up. Now when I talk about relative frequency, I'm not talking about a single value. I'm talking about a whole interval, because the class is now an interval of values. So how do I use the relative frequencies to compute the mean? The answer is, what I'm going to do is I'm going to take a representative value in each class. I'm not going to go in and find all the different values in that class. That's what I did really when I added all these up and divided by 25. I'm going to take a representative value. What I'm going to do is I'm going to take, in each case, the class midpoint. So here's what I will do. I will say the first class has a class midpoint of 3,099.5. I will take that number times its relative frequency, 0.04, plus the next class midpoint is 3,299.5, and I'll take that times its relative frequency, and let me go one more, I guess, plus the next class midpoint is 3,499.5 times its relative frequency, which is 0.32. Can I get another line in here? I think I can. Plus 3,699 times its relative frequency, which is 0.24, plus 3,899.5 times its relative frequency, which is 0.16, plus lastly 4,099.5 times its relative frequency, which is 0.08. Okay, it's a lot of work to write that out, but it's less work than it would have been to write all these out and divide by 25. So what I've done is I have taken in each interval, these 8 values here that have a frequency of 8 and a relative frequency of 0.32, I've not gone in and found out what those 8 values are. I've just taken the midpoint as representative of all of them. Probably some of them are bigger, some of them are smaller, but maybe that kind of balances out, and I just used the midpoint. I've used, 3,499.5 times that 0.32. Anyway, I've done that all the way through, and if I do that, I get 3,611.5. Well, not exactly the same as we got here, and we shouldn't expect it to be exactly the same since I'm using representative data, not the actual data in each class. So this is just an estimate of the mean, which I think we would call X bar because this is a sample, right? This is an estimate of X bar, and it's a pretty close estimate, wouldn't you say? So it actually does pretty well. It's only off by just a little over 11 pounds from the actual mean. And yes, I guess that's mainly all I want to do. I want to make one more statement here. I want to say that notice that classes that are intervals, they can work for discrete data as well. If I have a huge data set, let's just say with 1 million data points, and suppose they're all have values from 0 to 999, so they have 1,000 different possible data values. I don't want to build a histogram with 1,000 bars. That would just be hard to look at and summarize the data. I want to build it with maybe, 10 bars, something like that. Maybe you'd want to go as high as 15 bars. I don't know, but you don't want to have a histogram with 100 bars or whatever in it, so or 1,000 bars. So what you would do is instead of each data value, even though it's a discrete set of data, you wouldn't have each data value being a class, but you would pick another interval. You'd pick some interval, maybe from, if you had if the values were between 0 and 999, maybe you'd go from 0 to 99. That would be one interval. And then 100 to 199 would be the next class. And then 200 to 299, right? So I can write a relative frequency chart for discrete data using intervals as well. I don't need to just do it with singletons. And in fact, the examples I did before where the classes were all just single values are probably less likely to be the sorts of things you'd encounter in real-world applications. Most of the time you're going to be grouping data in intervals. And I left some space here to do the histogram, but you know what? I think I've done enough of those relative histograms. You have to do it to finish out these notes, and I did leave you an extra page to do that, but I don't think I'm going to do it. I think I'm going to stop here.